Hello guys, welcome back to my YouTube channel. I am back with another lecture on data science series. In this video, we are going to learn about dimensionality reduction. What is dimensionality reduction? It is the process of reducing the number of variables or features in a dataset while retaining as much information as possible. This helps in tackling challenges like multicollinearity, computational complexity, and difficulty in visualizing high dimensional data. Why dimensionality reduction? It is essential in data preprocessing and machine learning to address the challenges posed by high-dimensional data. Below are the key reasons. So first one is to reduce computational complexity. The problem is that high-dimensional data sets requires more computational power and time for analysis. जितने ज़्यादा डायमेंशन का डेटा होगा उतना ज़्यादा टाइम लगेगा और उतनी ज़्यादा पावर लगेगी. So reducing dimensions decreases the size of the data, leading to faster computation and reduced storage requirements. So, and to avoid the curse of dimensionality. So, the problem that we face is in high dimensional spaces, data points become sparse and machine learning models often fail to generalize well. So, the solution is dimensionality reduction, which mitigates these issues by projecting data into a lower dimensional space while preserving important information. So, and to remove redundant features, the problem is high dimensional datasets often contain correlated features which do not contribute additional value to the analysis. So, the solution is PCA, which is Principal Component Analysis, a technique which reduces redundancy by transforming correlated variables into independent components and then improve model performance. The problem is high dimensional data can cause models to overfit due to noise and irrelevant issues. The solution is dimensionality reduction. Now try to understand what is multicollinearity. It refers to a situation in regression analysis where two or more independent variables are highly correlated with each other. This can lead to several issues in statistical modeling, particularly in linear regression, where the goal is to estimate the relationship between independent variables and a dependent variable. So we can identify it by correlation matrix or variance inflation factor. So a correlation matrix visualizes the relationships between variables. High correlations between independent variables indicate multicollinearity. जितने भी इंडिपेंडेंट वेरिएबल्स है अगर उनके बीच में हाई कोरिलेशन होगा इसका मतलब है कि मल्टीकोलिनिटी एग्जिस्ट कर रही है. Similarly, for variation inflation factor, the VIF measures how much the variance of a regression coefficient is inflated due to multicollinearity. अगर VIF मास से ज्यादा है तो this also means that multicollinearity is present. Then let's try to get multicollinearity with variance inflation factor. Uh, this is the sample code. First we are importing pandas as PD, then importing numpy as NP. Then from stats models.stats.outliers influence import variance inflation factor. This is to calculate VIF of the dataset. So this is the example dataset x1, x2, x3, and y. So now you can notice that in x1 and x2, these both are highly correlated data. So multicollinearity might exist. So then we are converting a data frame, making a data frame using PD.data frame. Then we are computing the VIF. First we are making data frame of VIF, then feature is equal to x dot columns. Then we are calculating variance inflation factor of x dot values and you're printing the VI. So let's copy this code and paste in our Jupyter notebook. So now you can see that we are getting the feature as x1, x2, x3 and VIF equal to, yes, so INF, INF. Okay, so now you can see the output we are getting is um, in feature x1 and x2, it is VIF equal to infinity, which suggests that very much high multicollinearity exists. And for x3, it is 54, which is greater than 5. So here also multicollinearity exists. Now let's move forward with the presentation. Now let's understand what is principal component analysis. PCA transforms data into a smaller set of uncorrelated variables called principal components. It is technique used to reduce dimensionality and maximize variance. The principal component captures the most variance followed by subsequent components and data visualization. PCA simplifies data visualization by reducing dimensions while retaining most of the information. Now, this is the implementation of the PCA. Let's try to understand it. First, we are importing NumPy as NP, then Pandas SPD, then Matplotlib.pyplot as PLT, then sklearn.datasets, load eres. So, we will be performing PCA on eres dataset. And then from sklearn.decomposition, import PCA for performing PCA, and sklearn.preprocessing, import standard scalar. Standard scalar is required here to convert mean to 0 and standard deviation to 1, which is required for PCA because it is sensitive. Then we are loading the Iris data set, and x is equal to iris.data. These are the features, and y is equal to target variable. And we are standardizing the data using standard scalar and fit and transforming the data using fit transform. Then applying PCA, we are reducing the reducing it to two dimensions. Then PCA dot fit transform for transforming the model, then creating a data frame for PCA results. Data is equal to XPCA. Then we are plotting the PCA results. These are the PCA results, PLT.scatter, and we are explaining the variance at the end, which is PCA.explained variance ratio. We will see that the first two components will have the most variance, the first one the most, and the second one followed. So let's copy and paste this code in Jupyter Notebook. Now you can see this. These are the required imports. And we are loading the Iris data set. This is X is feature, Y is target variable. We are standardizing the data. Applying PCA, we are reducing the dimensions to only 2 by passing n components equal to 2. And we are creating a data frame for the PCA results using pd.data frame. Then we are plotting the PCA results. Then at last, we are printing the explained variance ratio. Now we will run this code. So now, as you can see, this is the output. We are getting PC of either data set, and you can see explained variance by each component. So the first component, it is the most, the second it is second most, and first and second are taking approximately 94 or 95% of the data. So let's move back to PDF. Okay, so we have seen the PC implementation. That's it for now. मिलते हैं अगली वीडियो में. Till then, keep learning, keep exploring, and thank you for watching.